We want to show how indeed Ramanujan's famous nested radical theorem works. So as you can see, this is what he proposed, and we have to check this. We have to check this and make sure that it's not a seeming pattern, but it indeed is a theorem, right? So first, note that 3 can be written as square root 9, which is equal to 1 plus 8. And why 1? Because you can see 1 in there, so this is what tells me we should write it 1 plus 8, and then 1 plus 2 times 4, 1 plus 2 times radical 16, right? Radical 16 is 4. So notice that we already have a second radical, right? A nested radical. Let's keep going. 1 plus 2. Now, as you can see in the formula, we have in the nested, again, starting from 1 each time, right? So we have to have 1 plus 15 to express 16. Then we have 1 plus 2, radical 1 plus 3 times 5. Okay, so notice 3 is exactly 1 greater than 2. 5 is exactly 1 greater than 4. We have 1 plus 2, radical 1 plus 3, radical 25. There we go. So you see there is some kind of pattern. That's a second nested radical, right? So you have perfect squares, 25, and then 16, right? So notice that if you want to show that indeed this is a never-ending pattern, that indeed you will keep going this way and you will achieve these results, you have to decide what you're going to prove, what you're going to show as being equal. And that's going to be this part here. Just showing this is equal to this will suffice. Okay, will be sufficient to deduct that indeed there is a pattern. And now, not only we're going to show that 2 radical 16 is the same as 2 radical 1 plus 3 radical 25, we're just going to let n be equal to 2. Okay, let n be equal to 2. Because n can be also set as 3, right? Because basically we can work with 3 radical 1 plus 4 radical 1 plus n, etc., instead of 2 radical 1, right? We're just assigning the arbitrary n value of 2, right? So we have to show n radical n plus 2, but n plus 2 is 4, but we got to square that. We have to show this as being equal to this part, n plus n, because n is 2, radical 1 plus, now 3 is n plus 1, n plus 1, radical n plus 3 squared, right? Because n plus 3 is 5, right? So n plus 3 squared. Okay, so does that equal to that? Well, let's see. This can be equal. This can be written as n radical n squared plus 4n plus 2, which is equal to. Now, what is this equal to, by the way? Well, this part is equal to n plus 3, right? Because squaring, taking the square root of the square of n plus 3 is n plus 3 itself. Right, so we can show it as n squared plus 4n. I'm sorry, this is this should have been plus 4. I don't know why I wrote plus 2. This is plus 4. Okay, plus 4. Okay, so notice that we can split 4 into plus 3 plus 1. And that way we can put this 1 as it is on the right side. So we can have n1 plus n squared plus 4n plus 3. Okay, let's see. So we need 1 plus, and then we need n plus 1 multiplying n plus 3. N plus 1 multiplying n plus 3. Okay, so we need let's see. So we need to split the 4n. N squared plus 3n plus n plus 3. You see, I'm just splitting so we can factor this part by grouping. Right? And then we're going to get what? We're going to get n radical 1 plus n times n plus 3, right? Do you see the factoring by grouping now? Plus n plus 3. Right? So I can group it like that so you can see the coefficient 1 and n. And that is equal to what? That is equal to 1 plus n plus 1 multiplying by n plus 3. Right? Because both n and 1, when added, they both multiply n plus 3 together. So we can group them together and they both multiply n plus 3. So now look what happens. Something really amazing. We have 1 plus n plus 1. And n plus 3, as we decided, can be written as square root of the squared n plus 3. Because the square root of the squared n plus 3 is n plus 3 itself, like it was before in the previous step. So bingo, we just showed indeed that for any value of n, we just chose n to be 2 so that we could express these numbers here in terms of n. But in reality, you could have chosen n is equal to 3 because the pattern seems to repeat. So you could choose n is equal to 3, and n plus 1 would be 4 in that case, and n plus 3 would be 6 in that case, and you would have showed that indeed this was true, right? So this shows that it's not just a seeming pattern, that indeed this is a theorem, right? Indeed, if you keep going, you will just work with perfect squares. 16, 25, the next one will be 36. It will be a longer expression, of course, right? It will be up to here. But in any case, you have successfully showed that the theorem holds. Hope this was helpful. Thanks for watching, and I'll see you in the next video.